Pablo and David were in the previous fight. To remember Pablo, David, and Jessica is another thing. It's more complicated.
Okay. So it's about the numbers of monkeys that were implicated in the fight.
That's correct. Okay. So now what we do is we've posited that these are 3 potential causal models or strategies that the individuals are using to make decisions about whether to join a fight. Now we want to test that. How do we test that? We've already collected our data. You know, we can't manipulate the system on this scale. So what we do is we build a simulation in which we allow individuals in the simulation to only play one of these strategies, so only C11, or only C12, or only C21. And we only allow the individuals to play those strategies who have significant delta P's in the real data associated with those strategies. Okay. So the simulation is highly parameterized by the data. And in fact, that's, as we'll come to in a second, that's a bit of a problem because we're pulling, in effect, many parameters out of the data. And we want to reduce that number. There's thousands and thousands of delta P's. Okay, so we build a simulation of C11 in which we allow individuals with significant delta P's for C11 to have conflicts. First we draw a seed pair of individuals at random, and then we allow all the C11 delta P's to run forward in time. And what that generates is a distribution of fight sizes, cascades effectively. And every time it dies, we pull a new, the cascade dies, we pull a new seed pair, and we let it go again. We do this thousands of times, and then we have this distribution of fight sizes. Okay? Does everybody understand that, the basic logic of the simulation? Anyone have a question about it?
Sorry, I didn't understand. Do you recompute the C for the delta P for each iteration?
So the delta P's are given by what's in the data.
Yeah, but do you take the result of the first fight to, or of 2 fights to update the value of
no,
delta P?
The delta P's come from the data. We never update them in the simulation. Okay. So we're just asking, given the delta P's that we observe in the data and these structures, these causal structures, can we recreate the distribution of fight sizes?
Yeah.
So can we recreate the distribution if individuals are only playing C11? Can we recreate the distribution of fight sizes if they're only allowed to play C21? And so forth. All right? So we're effectively running 3 simulations, one for each model, causal model. Okay, so you've seen this red line in previous graphs. And this is the distribution from the data of fight size. Now, for C11, this is the confidence interval, and then the distribution of fight sizes is in here, generated if the individuals are only allowed to play C11. And you can see it's a very poor fit to the data. So we conclude from that they're not playing the primary strategy anyway, that they're playing is not C11. They may occasionally be playing it. We're not testing combinations of strategies. C12. Okay, so the yellow line here is C12, and as you can see, C12 generates many small and many large fights. The same is true for C21 OR. I have for some of them the AND and the OR combinator, but not for all of them. But the C12 AND and OR are similar. So, as you can see, C21 OR, the conflict-averse version of C21, also generates many large and small fights. Doesn't fit the data at all. We find that C21 AND actually fits the data reasonably well, better for the smaller fights than the larger fights. It's a bit noisy here. That's probably because we don't have enough data. There are many small fights, but not many large fights in the data. So it's harder to fit for the larger fights. So what we conclude is that the primary strategy that the animals are playing, decision-making rule they're using, when they're deciding whether they should join a fight, is C21 AND. So they require a lot of animals in the previous fight to say join the fight, and they have to have there are significant correlations with them. Okay? How am I doing on time? Okay? All right. Okay. So now we have strategy is. But there's another very important thing that we learned from this. Can anyone tell me what it is? It has to do with the collective consequences of these strategies.
They are adverse to conflict.
So this does suggest exactly that's one important thing. The monkeys are averse to conflict. They're using the AND combinator or some variant on it. There's something else though. But the simulation, not the data so much, but the simulation tells us about what the implications of these strategies are for collective dynamics. So what it tells us is that if you play the strategy C12, you're going to generate some very, very large fights. If you play the strategy C11, you're never going to generate large fights. They're almost always going to be small fights. C1, C21 and is somewhere in the middle. So it tells us the implications of different strategies in our space of strategies for collective conflict dynamics. And it turns out that the size of conflict matters. Individuals pay a greater cost, on average, for large fights. Okay? And that's what this slide shows. So the mean contact aggression received, and that means individuals receiving slaps and punches and bites from other monkeys, which often leads to injury, is higher, significantly higher for larger fights than it is for pair and triadic fights. And the redirected aggression, which is basically Pablo and I have a fight, and then I attack David, because I'm such a nice person, is also higher when fights are larger. The likelihood of redirected aggression goes up. So large fights matter. So if you play, if you're an individual, or you're living in this group, and you decide to play a strategy like C12, the consequences of playing that strategy are twofold. One is that you might be able to, say, tune your local interactions better, because it's a triadic tuning. You're tuning to what your competitors and allies are doing, because you can consider how they're interacting with each other. So locally it might be quite good, but the long-range consequences are that you're going to generate larger fights, and you're more likely yourself to become the recipient of aggression, to pay a cost. So there's this trade-off. So what we can understand by studying strategy this way, in the space of different strategies, is what the implications are at the individual and the collective levels for those strategies. And we see that they have fundamentally different consequences for collective dynamics. And so a question you could ask, you could compare, there are lots of macaque species, there's 20 or so, and they have very different social systems with different levels of conflict. And so you could ask, are rhesus monkeys, very aggressive monkeys, playing the C12 strategy? Or does that account for the high proportion of aggression in those macaque groups? And our pigtails, which are more conciliatory, more friendly, they are playing C21. Is that the reason why? So we can start to compare the decision-making strategies in different groups and ask if that accounts for these collective social patterns. Okay. So if you remember, one of our goals is to construct the causal network. Now, these are very different kinds of causal networks than in the Eric Davidson sea urchin case. But they are causal networks based on our decisions. And what we find is that the C21 and bipartite graph network, so over here, we have evidence for that as the causal network generating the time series that we observed. So again, in terms of our lattice, it's this strategy, so this degree of memory and coordination that seems to be the dominant, not the only, we can't say that, the dominant strategy, decision-making strategies individuals are using in deciding to join fights. Now, the next point I want to make, I'm not going to give much detail on, but I just want to give you a sense of the potential implications of this kind of approach. Okay? So we went from the raw data to a correlation network to some understanding of which strategies the animals use and what their implications are for collective dynamics. Now, what we're trying to do now is associate those strategies with, or position them, as David mentioned yesterday, in the Chomsky hierarchy, which is a computational framework that has a strong mathematical basis for thinking about or computing the computational complexity of different kinds of production rules, as they're called in linguistics. You can think of these as, instead of language production rules, behavioral production rules. And we don't know exactly how this works yet, but if we can find a computational framework, like the Chomsky hierarchy, to position our rules in, then we will be able to say something about the computational complexity of those rules and to start making strong comparisons, strong principled comparisons across different systems. Okay. So to summarize, what inductive game theory provides is a method for quantifying the diversity of strategies or decision rules in competitive interactions. So we don't yet know much about what combination of strategies the animals might be using, and they're very likely to be using some of these other rules in certain cases. We don't know what the implications of that, using that diversity are yet, but we can quantify the diversity of strategy space. And these decision rules can be used to determine the causal network of interactions that underlie the collective phenomena. This facilitates quantification of the implications of different strategies, and as I said, potentially of a combination of strategies for collective patterns. And the cost of strategies and strategy diversity can be measured at the individual and the aggregate levels. Right? So we can ask, what are the consequences of using a particular strategy for the size of a cascade, series of conflicts, or the distribution of fight sizes generated? And finally, as I just mentioned briefly in the previous slide, if strategies can be linked to existing computational frameworks like the Chomsky hierarchy, we'll be getting a little bit closer to the sort of Eric Davison, at least at 20 or 30,000 feet kind of approach, and we'll be able to compare the computational complexity of these different strategies in very different systems. Okay, so I'll stop there, and then part two today is going to be about heterogeneity in state and timing, and their implications for critical social functions.